Okay, we're going to do some more related rate problems. I can get another example here. Another common one that we have is what's known as the shadow problems. Very common in all calculus textbooks. And what we have here is a shadow problem where a man who is 6 feet tall, all right, is walking at a rate of 5 feet. Let's see, 5 feet per. What does it say? 5 feet per second. Okay, there we go. 5 feet per second. Away from a light. Away from a light. Okay. Now that light is. The light is 15 feet high. Okay. And what happens is, since it's 15 feet above the ground, or 15 feet high, we want to figure out, all right, when he is 10 feet, all right, from the base of the light, okay, we want to figure out what is the rate at which the tip of the shadow is moving, and then what is the rate of the length of his shadow changing. So the first one we're going to figure out, all right, some different questions, is we're going to figure out what rate is the tip of his shadow moving. All right, so what is the rate at which the tip of the shadow is moving? All right. Okay, so here we go. Sorry about that. I should probably wrote this out before, but I will. When we have this, what we have is we have a man who's 6 feet tall, so we're going to draw a picture. All right, so we're just going to stick a little figure. 6 feet tall. We have another light post right here, and there's a light that is shining on this guy. He's a happy guy. All right, and it creates a shadow. Okay, it creates a shadow. Now, with this shadow, he is 6 feet tall, and this light is 15 feet high. Okay, and we want to figure out how is the tip of his shadow, because here's his shadow. Kind of envision on the ground, probably a little bit bigger than that. All right, here's a big old head. All right, where is the tip of the shadow? How is it moving? Well, when we have this, we're going to have a bunch of different things that are changing. Okay, first off, this man is walking. All right, his tall walks at a rate of away from the light, so he's walking away. So he's going this way. All right, so as he's moving this way, something is changing. All right, something is changing. Well, what is changing is at this distance right here, we'll call this distance A. All right, this distance is changing, dA dt, okay, according to a time he is going at 5 feet per second. Okay, so 5 feet per second. Okay, now we're going to figure out, all right, when he is 10 feet from the base of the light, okay, so when A equals 10, how far or how much is this shadow changing? Now the shadow we're referring to, the tip of the shadow, is going to be this length from here to here. Okay, so how is this length right here changing? So the tip of the shadow, how is that whole entire length changing? Okay, and we can call that, we'll call it S for shadow. Okay, for the tip of the shadow. Okay, now to figure this out, what we have are some different things we can do. Okay, and the first thing we have is, well, you notice that we actually create in this, and this is very true with some, all right, shadow problems, is we actually create two right triangles. All right, two similar right triangles. And you notice right here. And because we create two similar right triangles, what we're going to do is we have to figure out an equation. Whenever you do a related rate problem, the first thing you have to do is figure out the equation after you write everything out. And the equation we're going to use is a proportion. We know that the base of this big triangle, if you notice right here, okay, the big one, all right, that 15 is the base of that, and that is related to this smaller triangle, make that in green, all right, this smaller triangle right there. So 15 is to, I'll put this, is to 6 as, well, if you look at this, right, this is the whole thing, so we're going to say this is the S, is to, and we have this length right here. So we want to know, all right, this is the length we're referring to right there. Well, that length's going to be, well, if you think about it, it's going to be S minus A. All right, S minus A. okay, because A changes. So S minus A, those aren't 5, those are S's. Okay, this is an S, this is an S minus whatever A is. Okay, and that will give us the length of this green part of our similar triangles. Okay, well, from here then, okay, is now we're going to try to solve this. Now, to make this a little bit easier, we are trying to figure out how ds dt changes. So we're looking for ds dt. That's our question mark. Well, to do that, we're going to do a little bit, make this a little bit easier, is that we're just going to cross multiply. We're going to simplify this a little bit. We're going to have 15s minus 15a equals 6 times s. I'm going to now subtract these and get everything on the side. So I have 15a equals, subtract that, I have 9s. I'm going to now solve for s. So we have s equals 15a over 9, which actually can be simplified a little farther, which is going to be, we have 5a over 3 equals s. This is the equation that we just simplified for. To solve for ds dt, all we're going to do is differentiate it now, because that's what we're looking for. If we differentiate this equation, which is found from our proportion way in the beginning, remember this is the proportion we set up and simplified, we get ds dt equals 5/3 of dA dt. Once we get our derivative, we can then plug in our values. We know we're looking for ds dt, and we know it's going to be 5/3 of whatever dA dt is. Well, dA dt we find out is 5. And so we're going to have our answer 25/3 feet per second, I believe, all right, is what that answer, that's how much the tip of the shadow is changing at that moment in time. So now we have another question in this problem. Okay, so that's for the tip of the shadow. How is the shadow changing as he's moving at that moment in time? All right, so the shadow, let's just call this a different value. All right, let's call this B. All right, so this whole thing is A, and this little part, let's say, is B. Well, how much is the shadow itself changing? This just shadow itself. Well, once again, we can set up a proportion. All right, so how is the shadow itself changing? So this is going to be a little box. How much is the shadow changing? Oh, which is, or what is the rate? I mean, I should say, what is the rate? Is the rate of the shadow at that moment in time? All right, well, we'll set it up again. We have 15 is to 6. All right, so now, remember this is A. We're going to take as, all right, since we know what ds dt is, we probably could use S as S is to B. In solving this, all right, we can solve for, we're looking for B, so we know that 6/15 times S equals B. If we differentiate this, dB dt equals, oh, we simplify that. Take out a 3, we have 2/5 times ds dt. I just simplify that so you know. And we know that ds dt is 25/3. So doing the same thing, just finishing this up. So the shadow is changing dB dt at 2/5 of whatever ds dt was. 2/5 times 25/3. We have to cancel 5. We have 10/3 feet per second. So the tip of the shadow is changing, all right, differently than what the actual shadow itself is changing. Okay, so moral of the story, shadow problems. When you ever have a shadow problem, identify a proportion, all right? Identify what are the different values that are changing, what are the different values that we have, all right? And also use proportions. That's the key thing. Differentiate it, plug in the values, and you can find your answer. So I hope that helps you out. Good luck and God bless on all the wonderful shadow problems you find in related rates and in calculus.